You ready?
Okay, good afternoon, everyone. I'm Mars. I'm going to co-chair this afternoon session. And first on deck is our invited speaker, Laura Buchanan. She's going to talk about investigating transfer-tuning objects, insights from call-losses and dynamical modeling.
Hello everyone, thank you for the introduction, Mars. And yes, I'm going to talk today about colours and their origin positions in the ASIAA system. So to begin with, colours. It doesn't quite look like this in the ASIAA system, but it is similar. We've got different shades of red, probably different shades, but we've got one nice picture, so I may as well reuse it. We've seen lots of talks with beautiful JWST spectra, and this one's been presented on Monday. There's a poster outside, so you've got beautiful spectra of cold classical TNOs and some neutrinos. And as lovely as these are, unfortunately we do have to share these big telescopes, so we can't just point them at every TNO there is. So in order to understand the compositions of large numbers of objects in the ASIAA system down to reasonably low radiuses, we need to use colours. So what this means is that we take photometry in little wavelength bands rather than big spectra. And you can see this is an example of the three which I'll talk about today: two optical, G and R, and one near infrared, which is J. And although we're looking in less detail, it's essentially a great deal less of resolution spectra, looking at this region of the spectra is enough still to distinguish between, say, for example, these cold classicals, they're sharper slopes in the optical, versus some of these proteins which are very flat down here. So we can still make big distinctions on their surfaces. And so we've been studying the colours of objects in the ASIAA system for a long time. You can see an example here from Tegner et al. 2008 of the colours on centres, which show this bimodality in that optical colour versus just number. So this bimodality of optical colour we've kind of known about for a while. So I've seen in the centres just because they're closer and brighter, but there's been lots of colour surveys since which have shown this out in the TNOs as well. You can see this example from the 2016 paper of centres and TNOs with this bimodality in colour versus H magnitude, so small objects up here, big objects down here. And the colours which I'll talk to you about today come from a specific colour survey called Colossus, or the colours of the ASIAA system origin survey, because it's always fun to have an acronym of an acronym. So this survey took observations between 2014 and 2022, so quite a long period. It started while OSOS was still discovering, which was quite cool. It takes a subsample of OSOS TNOs, so only from certain observing blocks of certain region of the sky, and only TNOs that are brighter than 23.6. Just this brightness limit means that we can get better photometry for the colours. And so these are reasonably small TNOs on 100 or so kilometre in size. Nicole did introduce this before lunch, so you might remember that, but this is data from the main survey, which is the near simultaneous optical and near infrared observations taken with Gemini Nova 92 TNOs. And by near simultaneous, it means that the entire observing sequence, so from start to end in a series of bands, it takes place over quite a short amount of time relative to the typical light curves of TNOs. And so we can do our best to reduce any light curve effects in these colours and hopefully reduce any errors because of that. And although I'm talking about these GR and J band observations before lunch, Nicole presented the simultaneous U band from CMHP, and then later on this afternoon, Cameron should be including some of the Z band as well from Colossus. So what do the colours actually look like? Here you have your optical colour, so G minus R down the x-axis, and then R minus J near infrared up on the y. These points and colours are just related to the OSOS dynamical classification. So you can see solar colours down here, lots of dynamically excited objects, lots of cold classicals over here. And historically we see this bimodality, which has been referred to in a lot of different ways. You've got blue and red, you've got neutral and red, you've got less red and red, or perhaps accurate one, which is red and very red. This, I say, is most accurate because remember, these are solar colors. All of these are some shade of red. It's just some of them are higher up that scale. In this particular case, though, I'm actually going to refer to them as blue and red because it means that later on I can do this with my points and keep things nice and clear. But yes, I think Nicole also briefly mentioned that from Colossus, it was proposed that there's an alternative way of an alternative surface taxonomy that you can make using the optical and near-infrared observations, because keep in mind that this bimodality, that's only in the optical. Although we were plotting near-infrared colors here, it could be a different band, it could be I or Z, and you'll still see this bimodality. Well, if you take into account this solar reddening line, which Nicole had some lovely little figures that showed how it works. If you have a straight line on the line, you've got relatively higher in near-infrared above the line, relatively lower below the line. And from that, you can therefore reclassify. And keeping in mind, this isn't just saying red and blue can be split differently. This is a whole different surface taxonomy where you need near-infrared to define this. It's probably better shown if you actually inject along the solar reddening line. So that would be a line straight across at 0 here. And you have this bright IR class, which are relatively bright along the wavelengths, keeping in mind, of course, that everything is relative. So they're not necessarily bright in the IR, it's just relative to the other objects. And those are faint. And as you can see, the faint IR is predominantly made up of cold classical surfaces, while the bright IR is a much bigger mixture. And throughout this survey, there's been lots and lots of previous results of cool things, interstellar object colors, correlations, which have been previously discovered as well between inclination and color, the presence of, I'll talk about later, blue binaries, which are these neutral filament binaries which help put constraints in the formation of the outer solar system. Some of the more recent ones, such as the definition from the full Colossus data release, the definition of these bright IR and faint IR surfaces. And how, if you instead use the bright IR and faint IR surfaces instead of just red and blue, you can better define what the primordial disk might have been like. So, for example, from this 2023 paper from Mikhail Marcet, you can see that there's actually, even just within the bright IR class, there's a correlation between inclination and spectral slope, meaning suggesting that there might have been a gradient in the primordial disk. Or you saw this figure, I think, in one of the talks earlier about the distribution of these different surface classes on the mean motion resonances and how you can maybe infer stuff about how the resonances were captured throughout the period of planetary migration in the early solar system. So back to the title of my talk, which is combining Colossus observations, which, thanks to the fact that they're based on Colossus discoveries, are fully characterized and so go along with them by surveys, which lots of people have described before, and some dynamical models of the formation of the outer solar system and the formation of the Tau as we see it today. So you can see in this wee schematic down here, this is again just the Colossus colors, so you've got 5 giant planets pre-giant planet migration, some massive planetesimal disks, which the hot TNOs that we come from, somewhere out here called classicals. In this case, it ends at about 30 because we actually haven't stopped migration, so there has to be less material out there so that it stops scattering and therefore stops. And these bluer and redder surfaces are a result, we think, of where they formed in the outer solar system. This has been covered in a few previous talks, which is the nice thing about a TNO's conference. We are all thinking the same questions. But in addition to the typical optical surface split, we also have this IR class surface split of your bright IR and faint IR surfaces, which similarly we believe are a result of where the objects formed in the early solar system. But then the question becomes, okay, where did they come from, where would this split be, and what can that tell us about the primordial solar system that we can no longer see? And in order to investigate this, I've used a couple of different models. These are both from David and Esconi. The first one's from his 2016 model, which just has a single condensed disk between 24 and 30 AU. And then the second model is from 2020. And although the disk does significantly drop in density beyond 30 AU, there is a low mass disk extension, so you've got material coming out from material out towards the cold classical region that's the hot population can come from. And from this massive planetesimal disk, you can see in this very accurate schematic of the Nice model. In this particular case, you've got an ice giant in here. There's some instability between the giant planets, and we lose that ice giant and get parallels you see it today. We, of course, lose a lot of material as well, but we end up with this mixture of dynamically cold TNOs that we think formed roughly where they were, and the objects in the massive planetesimal disk, which are now dynamically excited and mixed among those dynamically cold TNOs. And we can actually use dynamical models to investigate where these objects would start and end, and where different surface colors assigned based on where they started might end in the kind of today, and then compare that with observations from Colossus. So I've got here, this is the sample of Colossus which I'm comparing with. You can see it's very slightly different based on the dynamical model, because I'm, in this case, I only want the hot population, because you want them to be in place by Neptune, there's no point in the cold ones. And the dynamical models only include the hot population. And additionally, we're taking out centers because the math has some surface reprocessing, taking out the motion resonances, because although we know where they come from, the dynamical model, the motion resonances we observe with Colossus are likely a mixture of cold classicals and hot populations, so you can't actually split them, and we really want to be comparing apples to apples, not apples to oranges. So, how does this actually work? Well, once we've assigned colors to objects based on where they start in the outer solar system, you can then bias them to what Colossus would have observed. So this just means running the OSSOS survey simulator to create a virtual OSSOS. And only taking the observing blocks that Colossus looks like, so that's a small subsection I've already shown before here, but this is a total of 6. Which you can see are different areas in the sky relative to the ecliptic. And then make sure that we only have objects starting from 23.6, which is again the same color as made Colossus, and same dynamical cuts, so just essentially making them as similar as we physically can. We're run until we have lots and lots of detections in each observing block, calculate some probability of this particular simulation matching the observed colors from Colossus, and then making a combination of all of this together. And so you can see an example here of what that might look like. So this is, well, I'll get onto it later, these are the two most likely scenarios that will create what we see today. Down here we have the transition position, so that's the place in the primordial disk that the split in the either red hair or grey hair surfaces, or the blue and red surfaces would have been, versus the combined probability from all the observing blocks. You can see both of them have this peak, so a most likely position, along with the grey shaded region just showing that 95% confidence. So in this particular case, I investigated a range of scenarios because although we, like for example, we think that cold classicals have faint IR surfaces, it's very unlikely that you have an initial disk composition that starts faint IR, bright IR, and then goes faint IR again. But it's still nice to prove that it isn't possible, that it doesn't match the observations. So these are the numbers that come out of everything, but we have additional constraints from lots of observations of the outer solar system that we can use to rule out or confirm different numbers here. So yeah, you can see here, additional constraints, a few of them. First is the formation of the blue boundaries. So like I mentioned earlier, these are blue surfaced or neutral surfaced binary objects which are around cold classicals, and because of the wide setness of them, like we don't think they could have created these binaries post-planet migration. They must have formed in these binaries and just maintained it since then. But because they're binaries, we don't think they could have survived some significant pushback from gravity in a solar system to roll all the way out without losing that binarity. So in order for these blue binaries to exist, you need blue, or they're also bright hard as well as blue. You need those surfaces to exist beyond 30 AU, not only exist within that. And to be clear, David Nisconi did do some simulations in 2022 and did show that further out formation is better for their survival. So although they can technically survive at 30 AU, ideally you want it further out. But either way, it does rule out a couple of cases for certain. There's no blue material beyond 30 AU in either of these cases, or granular material. They can't create the blue binaries, so those are absolutely not. We've got Neptune Trojan colours. There's a talk about this later on, and there's a place for outside in the colour of Neptune Trojans, but up until the last couple of years, all of the Neptune Trojans with observed colours showed, all but one of them showed blue surfaces. So you can see this very accurate schematic of Neptune with some Trojans and just one red one. But in more recent years, we have people have taken additional observations, colour observations of the Neptune Trojans, and I can show that I have detected additional red surfaces. So in order for these red surfaces to exist on the Neptune Trojan orbits, they need to have red material further sunwards so that they could end up further close to the sun. And again, this isn't accurate with the numbers, but if you want to, I think, see the real numbers later, you can see either the poster outside or a total later this afternoon on the Neptune colour conundrum. But yes, either way, in order for us to satisfy the fact that the Neptune Trojan colours are like this, you need to have redder surfaces that are forming within about the 30 to 35 AU region. So once again, that means that there's some objects, some surfaces, surface compositions, surface layouts, that cannot create it. I put a yellow cross because technically the number 30 to 35 AU only applies to a single a single blue-red disk, but you can still say no, there wasn't any red material. There wasn't enough blue material further in, so that's unlikely. And unfortunately, the Neptune Trojans don't have those J-band observations to categorize them into the faint IR, bright IR. You could probably postulate that most of the ones that are blue are probably bright IR, most of the ones that are red are probably faint IR just because there's a big overlap in those classes. But I didn't want to say that for certain. It's likely that these are okay, but again, you don't want to say things for certain. But yeah, the third constraint then is that there is this distribution with both inclination eccentricity versus spectral slope versus color. So you want to have more bright IR surfaces on high inclinations and more blue surfaces on high inclinations, and the faint IR and red ones on low inclinations in order to match the observations. Unfortunately, in my particular work, we can't say for certain. I did try and test if the outputs from my models were consistent with the inclination distribution from Colossus, and it was inconclusive, probably just because we have reasonably small numbers, so it couldn't get it to your statistical significance, but we can still kind of infer because part of the problem with that is the fact that from the dynamical model, the inclination distribution doesn't perfectly match the inclination distribution from the carousel itself, so it's not super unexpected, it's going to have trouble. But yeah, David, this is what he did show with his models, that objects that form further sunwards or further into the solar system preferentially end up on higher inclined orbits. So that means most likely that if the bluer or if bright IR surfaces are further inward, they're going to end up in higher inclinations, even if we can't say that for certain. But I guess from all this, we have a couple of cases which can't be ruled out. We've got your inner blue, outer red, the extent of this model, and your inner bright IR, faint IR for your extended this model again. So I circled this one in green because it was all ticks. This one's kind of green and yellow because one of them we couldn't say for certain, but was probably yes. And I guess what would this actually look like on the primordial disk itself? You can see this is just a simple schematic of what that primordial disk looked like in the extended disk model. You've got your initial second major axis, which extends out goes 40 plus AU versus surface densities. This isn't the number of objects, it's just there's more objects up here. There's some drop in density at about 30 AU, and then you continue slowly dropping throughout. And based on this, it looks like over here we'll have blue or bright IR, and over here we'll have red or faint IR. And in here, this is where those kind of uncertainties overlap. So we're thinking that I'm thinking that the transition is somewhere in this region, which is, I think, quite an interesting result because it means that this kind of is in agreement with the cold classicals and the red and the painting art all being a single surface, which is, you know, nice to see. If I got the opposite way around, it would have been not very reassuring. So this is essentially the cold classicals might just be an extension of this low mass disk extension, and it's all just one material that's going out. It's also interesting because the place where our color transition happens also coincides with the big drop in density in the primordial disk. So it's like, this is just speculation, but perhaps there's slightly less collisional evolution out here because there's less material. Technically, this is something which you might be able to see in the size distributions, if there's some difference information out here. And in here, I have started looking at that, but the numbers aren't well enough to go in this yet, unfortunately. But if there's lower density of material for one surface versus the other, suggests that the formation might be slightly different. And then just as a little aside, since I was doing this work anyway, you may as well have a look at what the color ratio from Colossus tells you about the intrinsic color ratio within the chemical. So this was with the CVEP's L7 model, which I think a couple of other people have used. We'll probably do it again with the Osmos++ model once it's finished, but this is definitely good enough for now. This is much simpler. You just apply a color ratio, not ration, to the L7 model from CVEPs, and this has nothing to do with where it started, but it's just interesting to see, and you can use the survey simulator to see what Colossus would have seen, combine the probabilities. I don't have a pretty graph here, but it's just some numbers at the end of like a relative blue ratio of somewhere between 0.25 and 0.45 red objects to blue. I think the peak was about 0.3, which is a little bit higher than previous people have measured, but it's also important to note that I was working within a cutoff in H magnitude rather than a cutoff in size. And so bluer or brighter objects are slightly lower in albedo, so that would probably shift the ratio more similar to others. And then I don't have a number to compare against, but the faint hair, bright hair is a slightly bigger range, going to that are a higher value. And I guess I'll just finish off with a quick summary of what this is. Yeah, simulations comparing the primordial hyperbolic colors to the colors you see today, using two different formation models and looking at two different TNO surface definitions or surface taxonomies. We've got two kind of most likely initial layouts, both which use the low mass disk extension with these particular layouts. It's interesting, potentially, that the surface transition, the surface composition transition is in the same region as the drop in density. And again, this is consistent with cold classical surfaces coming from the tail end of the extended disk. And that's all. Any questions?
Thank you very much for the presentation. Do we have questions?
Thanks, Laura. That's very nice. That's not working. Thanks, Laura. That was very nice. I wonder if you could speculate or make any comment if your comparative sample were much smaller TNOs. What would you say about the color of this map and the beautiful block surface density versus
If all of the objects which we've observed were smaller,
Sure.
you're saying?
If the Colossus objects were 10 times smaller.
Okay. I guess it's tricky to say because we believe it's really instability that forms them and that that's going to create different things. But if they were smaller, maybe you'd see more blue ones because like you might have less radiation on the surface at smaller sizes and they're moving around, you might bump into each other a bit more and cause some difference. So, but it's very difficult, I think, to speculate on that just because we don't know for certain what's going on there. Yeah.
It's a nice talk, but you spell my talk, actually. That's all the question. So the question for you, and I think also for the disco team is that how is this bright IR looks in the spectrum?
How the bright hierarchy looks as a spectrum?
Yeah, I think it should be see something different, right?
Well, it's not that you'll see something different. It's a way of quantifying further into the spectrum than just the optical cutoff. So just the red blue which comes from the PR, so you're looking at the shorter wavelength part of the spectrum. By adding the J and turning it into this bright IR, faint IR, you're essentially looking at further in the spectrum, and is it increasing after the optical or is it decreasing after the optical? If that answers your question. Yeah.
Hi. Yeah, very nice talk. I think that your model is fully compatible with what we've seen with the James Webb in the transmit network, right? Clearly the colors in the visual are proxy of the composition of the different groups.
Yes.
The family, the bold, the double deep, and the cliff are blue, intermediate, and red.
Yes.
In your classification. So, and also, if we look at the composition of the cold classical in disco sample in India's talk, all of them are cliff.
Yes.
So the hypothesis in the disco paper is that exactly that we discriminate with the regions, information regions, due to the material, the ices that you can accumulate because of the temperature and pressure and different regions in the disk. So we pass from only accumulating water ice and CO2, only some carbonates and the more complex materials in the cold disk.
Yes.
So I think that this is very nice to have colors and the composition that are big.
Thank you.
Do we have more questions? Still have time for 2 or 3. Oh, right.
I'm going to ask you a more speculative question,
Yes.
because I don't know the answer, so you might. LSST is not going to get us the J-band, and so you've shown how important linear and
And so I was just wondering, what do you think in terms of how do we try to expand or translate between what you're seeing and LSST? What are the bands, or what is it that we should do if we're looking at the chemistry, looking at the colors, to be able to sort of pick out the interesting objects or test some of the things that you're looking at? So you thought about how with LSST coming online, what's going to be the most important filters for us to be thinking about or looking at?
Yeah, I suspect that some of this might be covered later in Gary Bernstein's book, because DES is similar filters to LSST. So I don't want to steal what he's going to say, but I think that the DES service classifications of bright near IR and faint near IR have some overlap with the Colossus ones which go up to J, because of course Z and color doesn't overlap with J is getting towards that region, so you're starting to make the same distinctions. So I believe that you could make similar speculation and investigation what I've done here using the vast number of LSST ones. The disadvantage there being that LSST photometry and colors is going to be to a much lower precision than Colossus. So you might have to make some adjustments based on the fact that our like spitting colors, spitting the IR classes may be a bit more overlapping just because of very large errors on